Okay, now, if you don't instantly see what the derivative and second derivative of this are, you really need to review your rules of differentiation. Okay? Chain rule, all that stuff. So make sure you got that. You can't live in any kind of technological society without never forgetting that. Okay, so you have L lambda squared A e to the lambda t plus A e to the lambda t over c equals 0. Okay? The A e to the lambda t is common to every term, so now you have L lambda squared plus 1 over c equals 0, so that lambda squared equals negative 1 over LC. And that should be pretty instant. And what's your solution then to lambda squared equals negative 1 over LC? Anybody but Elam answer me. Elam being in differential equations, we can answer. Not because I think he'd make a mistake and be embarrassed, but because he knows. Okay? What is it? Well, have your chance. Square root of negative, you know, you factor out the negative and all that stuff. You got to know the algebra of that. Really have it. And we're going to call that omega. It's 1 over square root of LC. Okay? So,
wouldn't you have two roots to that equation?
there's a plus or minus there. I'm sorry? Oh, you were just about asking me, wouldn't you have two solutions, because you know they have to have two solutions to a second order equation, right? Yeah, you got to have the plus or minus there. I didn't write it down, even though I keep nagging my precalculus class about it. Yeah. Okay, anyhow, your solutions. AE to the I omega, AE to the negative I omega. Okay? Now what's e to the I omega? I'm just going to say Taylor expansions for the exponential sine and cosine functions. This is also part of something you really want to have in your mathematical vocabulary. You want to understand this. So that's just a note. Be sure you understand this. Okay? Now, and, you know, what I wrote is perfectly correct, but it's not. And down here I said solutions, e to the I omega. It's I omega t, right? Because it's AE to the lambda t. And since you have solutions e to the I omega t and e to the negative I omega t, well, here's your, this is an ae to the omega t. Instead, we're going to use b for the constant. And this is of the form ae to the negative omega t. It's what we get for the e to the negative omega t. Then, using the fact that the sign is odd, this is going to be a minus I sign. This is going to just be a cosine omega. Yeah, just plain old cosine, right? Omega t. We get this. Okay? And b and c are arbitrary constants. Not only are they arbitrary constants, they're arbitrary complex valued constants, because we're into the realm of complex variables, which is what all engineering is done with. Okay? In other words, the most general way to express everything is very, very often in terms of functions of complex variables. Okay?
What happened to the negative omega t?
Even odd functions. Sine of negative omega t is negative sine omega t. So that c is going to be multiplied by negative sine omega t, hence you get the negative c here. Cosine is an even function, so cosine omega t. Negative omega t is just cosine omega t, hence you get the b plus c. Not saying that fast, you might have to go back and look at the video, but it's very straightforward. Okay? I don't necessarily expect you to put all this together. So b and c are arbitrary complex constants. So a cosine omega t plus phi is your general solution. Now again, I'm skipping things about double angle. Yeah, I skipped precalculus. Okay? And I don't expect to be able to do this whole argument. But you should understand that the only calculus that was involved here is taking the derivatives of e to the lambda t. Nothing else is, well, yeah, there's calculus involved in the Euler identity, right? Taylor series expansions of these things, which is something you need to be totally, you should always be able to, in your head or very quickly in paper, write down the Taylor expansion for e to the x or sine x or cosine x. Okay? That's just part of the vocabulary you're going to want to have. And if you do, you're going to be ahead of most people. Even most people in an engineering program at a very good school. Outstanding engineering program at a good school. Okay. The rest of this is just algebra. Okay. Algebra with complex numbers, but you learn that in pre-calculus. Okay. So the point is then that this equation, we have a whole thing on the screen anyhow, you know what the equation is, and I think most of it's there. In this equation, for the same reason, have the general solution I gave you at the beginning of the year for a simple harmonic oscillator. Okay? Now, I'm probably going to ask you for homework just to plug AE to the lambda t into the equation for this function, and that function is just for basically your RLC circuit, series circuit. There's a parallel circuit too, it has a different equation. Okay? You plug this in here, you're going to get a solution. And once we interpret that solution, you understand how this circuit works. Okay? And then we'll talk a little bit about resonance. Not to the extent we did in differential equations, that gets fairly hairy. Okay? Doesn't use anything more than precalculus, but it still gets pretty hairy. Okay? Yeah, just double angle formulas. Formulas you get from Euler identity. But again, interpretation and the limits are a little bit hairy, and I'm not going to put that on you. Okay? But get the general concept of resonance, which means, okay, this circuit has a natural frequency omega. A pendulum has a natural frequency, angular frequency omega, right? Well, you match that angular frequency in pushing the pendulum, and you're going to build up a lot of amplitude, right? Now there's a limit to how much amplitude because energy gets dissipated due to air resistance and mostly due to the flexing of the chain or whatever is holding the pendulum string. That's analogous to resistance in a circuit. Mathematically, they're identical. Okay? If you had no resistance in that pendulum, you'd have an unrestricted increase in amplitude. Okay? If you drive the pendulum at its natural angular frequency, you get maximum possible amplitude. Just like if you drive this at its natural angular frequency, you can build up a lot of amplitude. Okay? You build up a circuit that has a bigger and bigger current oscillating. And all that is really kind of important. And, a couple more comments. I'll just turn the camera off though.